How's lab 2 going for people? Got a thumbs up from Katie. Everyone else doing okay? Any questions or bugs or anything? Okay. I had one bit of feedback from one of the Monday groups, which was that it would have been helpful in lecture to sort of give a gentle push in the right direction of how to start putting together the column state machine. So I thought I would talk about that just a little bit as a place to start. I imagine most people have already started, but if you're having trouble getting this together, then maybe this will be useful for you. Let me just share my screen. And you can do whatever you want, and maybe some of you will have different methods for doing this that work for you. The way that I started putting this together and the way that I found to be most helpful to me is to start by, for a single column, creating and initializing 2 M10K blocks with information that is very easy to understand. So maybe for each M10K block, you put a 0 in the bottom row, a 1 in the first row, a 2 in the third row, all the way up to an N in the nth row. And then to start by building a state machine in which you attempt to start at that bottom row, read out of the M10K block directly above it, leave out the compute module at first, and just see if you can then move to the next row and properly move what was previously in the top node register into the center, what was previously in the center node register into the bottom, and then read out the new top node. And put all of that out through a model sim test bench. So put out the registers that are holding the top, center, and bottom nodes. And if you filled those M10K blocks such that they increment by 1 all the way to the top, then what you should get is 3 linear ramps where each one slightly leads the previous one. So your top node should lead your center node by 1, and your center node should lead your bottom node by 1. And then you can confirm that you're properly moving up those M10K blocks, right? Which is one of the harder parts of this state machine, is just reading and writing memory properly. If you can get that working and then insert the compute module into that infrastructure, that worked quite nicely for me. If anyone's been working on this and they built this up in a different way that they want to share, that would be nice to hear. But if you're looking for a place to start or to start debugging, maybe that's a good suggestion. Did anyone else have any strategies that worked particularly well or not well?
One other strategy I've seen in the past is to start by making a list of registers and memory blocks in one direction and then cycles in the other direction. And in every block, fill in whether there needs to be a read, a write, or both for each different memory, so that you can make sure that you never ask for more than one at a time.
Okay.
That's just colored pencils on paper kind of work.
And by the way, I want to, this is also just something that's based on feedback that I've gotten in lab. I want to reassure people a little bit that this lab that you're working on right now is, I think, the hardest one. And in particular, I think this week of this lab is probably the hardest checkout of the lab. So just in case you are sort of pulling your hair out thinking, oh my God, we're on some sort of like exponential ramp and pretty soon I'm gonna be living and eating and breathing FPGAs. The rest of the class is by no means easy, but I'm just reassuring you that we're not on some crazy ramp up. This is about as complex as a state machine. It is the most complex state machine that we'll build in any of the labs. You may build a more complex one for your final projects, but I just want to assure you that this is hard. This is probably the hardest checkout of the hardest lab of the course. Okay. And along those lines, by the way, we're going to do a little bit of logistical rearrangement for TAing this class, because as you've all discovered at this point, this class is a lot of work, right? And for groups of 2 and for groups of 3, it's a huge amount of work. Your TA, Katie, has been doing this class by herself, which for lab 1 was barely achievable. And for labs 2 and 3 is, we have discovered, essentially impossible without totally sacrificing quality of life. So the solution that we've come up with, that I'm just telling you so that it doesn't seem like we're being sneaky in any way or whatever, just doing things with the class that you're not aware of. Katie is going to join a group of 2. She will remain TA, which means in the Monday and Friday sections, she'll still be available to help out groups with debugging, which is awesome because she's been adding a huge amount of value doing that. But she will join the Wednesday group of 2, the Nicole and Alex. Katie receives no information as a TA that anyone else in the class receives, so there's no advantage in that regard. But even so, just to make sure that everything is fair, Katie's group will be graded outside of the curve. So if you know, they are able to produce 1 million nodes for the drum, which, you know, like I said, there's no advantage to being a TA in this class and being in a group. So even so, just to make sure everything's absolutely on the up and up, we'll grade folks on a separate curve. I just want to make people aware of that. And if anyone wants to talk about it, you can feel free to reach out to me, but I just want to bring that up. Any questions about this or anything else?
I heard one question in one of the sessions. The people were unsure of the physical meaning of rho and eta. When they actually got down to programming, they didn't know whether to make rho bigger or smaller or eta bigger or smaller to get a result that they wanted. Do
you want to talk to that a little bit?
I can talk to that a little bit.
Sure.
The rho is a scaled speed of sound. A bigger rho means a faster speed of sound, which means that the system propagates waves faster across the drum, and therefore the frequency is higher. So increasing rho up to 0.5 increases the frequency, and just below 0.5, where the system is still stable, you will find that the frequency is at the Nyquist maximum. In other words, there's 2 samples per sine wave cycle. It goes high, low, high, low, high, low. In other words, it looks like a damn square wave, not a sine wave. As you go down to a rho of a 16th or a 32nd, then you will see a sine wave with 16 or 32 samples on it, and it looks more like what you expect as a sine wave. As you go to a bigger drum, the frequency drops because the propagation distance is bigger. So a drum twice as big will have half the frequency, in which case you could increase rho a little bit. Eta is a damping term. The bigger eta is, the faster the drum dies out. If you make eta on the order of 0.1 or 0.05, the drum will go thump. It won't go gong, it'll go thump. A real bass drum has an eta of about 10 to the minus 4, which corresponds to a number of like 2 to the minus 11 or 12, but I would suggest using 2 to the minus 10 to start with. So longer sounds, lower eta, higher pitch, higher rho. Bigger drum, lower pitch. That's it.
Cool.
Any questions on that?
Okay, if not, I thought I would start by, last time I said that I was going to show the, not going to spend much time on this, but last time I said I would show the data sheet for the audio codec that we're actually communicating with, mostly just so you're aware of what it's capable of in case you would like to use it for final projects. So I thought I would just show you that quickly now. It's on the Lab 2 webpage. Here, the Wolfson WM8731. And I just wanted to show you the block diagram for this thing, just because it has a lot going on, a lot of things that you could play with if you wanted to. So I'll point out a few things. It has 3 inputs, so a right line in, a microphone in, and a left line in, all of which have individual volume controls, right? So you could sort of turn down the volume of one of your line inputs and increase the volume on others. It has, what else is of interest to point out here? It enables you to mix these various signals together. So you might be able to do something interesting with that. It has, a couple of interfaces. This whole thing is configured through that AV config module that we drag and drop onto the QSys bus. So that talks, as we've discussed, through an I2C interface that lives up here. In any case, you might think about doing some interesting things like this, like you know, you could attempt to do things like put music with voice in and either isolate the voice or isolate the music and subtract the other part out.
You could add one or two things. The digital audio interface is separate from the I2C. It's at the bottom of this diagram. And that's an 18 megahertz serial alternate left-right channel, up to 24 bits of sound per channel. That's a very high-speed interface. So the AV config runs the I2C. The audio interface module runs the high-speed digital interface. The one other thing which I found amusing was that the digital filter internally in this thing is good enough that you can't produce an aliased output from it. It filters away instantaneous changes.
So if you try to input a square wave, it'll smooth it out, is what you're saying. Is that correct?
It'll ramp it up and ramp it down for you. So this is a separate integrated circuit. It lives on the side of the board. It's its own state machine. You can manipulate it in various ways, but it's separate.
Questions about this? Okay. If not, what I want to spend the bulk of today talking about is how to create your own phase-locked loops. So it will likely be the case for your drum that you want to speed up the clock that runs your state machine, because that will allow you more samples between each 48 kilohertz audio sample, which means you can walk farther up the drum. So instead of clocking off of clock 50, which is what we've been using, you may want to create your own clock that's at 100 megahertz or 200 megahertz, or really as fast as you can get it to go so that you can build the biggest drum that you can build. There are a few different ways that you can do this, and I want to talk through basically every way that I could figure out to do this, in part because maybe you'll prefer one over the other, and also because doing this is another way for me to show some of the other features of QSys that we've maybe only talked a little bit about or not talked about at all. Things like creating your own subsystems to add to the QSys bus. I want to show how you might do that. So as a starting point, I have here essentially just a blank project The only actual Verilog that's in this project is shown here. All I'm doing is I have a 26-bit register called count that I'm incrementing at 50 megahertz. And every time it overflows, I am toggling LED 0 on the FPGA. We've done this a few times in various previous examples. I'll just open up the QSys bus and show you that there's really nothing on it except the system PLL and the ARM. And I believe I have this already on the FPGA. Yeah, so this is just blinking at approximately 1 hertz. And what I want to do is set up a few PLLs to blink these other LEDs at faster rates. So we'll build essentially, we'll do essentially copy paste the Verilog that we already have in there, but run it instead of running it off of clock 50, we'll run it off of our own faster PLL and see that the adjacent LEDs blink faster. And we'll do that in a few different ways. So this is all that is on the QSys bus. So just the system PLL and the ARM. And I want to add my own phase locked loop here to this bus. And as I mentioned, there are a few different ways to do this. Probably the easiest way is over here in the IP catalog under basic functions, clocks, PLLs, and resets, PLL. There's an Altera PLL module here. We can double click this and it'll add it to the bus. And then there are a bunch of configurations here. The ones to really pay attention to are what's your reference clock frequency that you're passing into this, and then what's the desired frequency that you want out of this. Right now, this is set up to a reference clock frequency of 100 megahertz. I'm going to keep it at 100 megahertz for reasons that I'm going to show you in a moment. And I'm going to say that the desired frequency that I want out of this is 200 megahertz. And then if you would like to, you can configure other things here. You can, for example, change the duty cycle, change the phase, do all sorts of things. Maybe you'll want to play with those parameters, but in all likelihood not. You probably just want a faster in-phase clock. So 100 megahertz input, we want a 200 megahertz output, and we can add this to the bus. The reason that, that I asked for a 100 megahertz input is I'm going to hook up the reference clock for this phase locked loop to the system clock. And if we look at the system here, that system clock is running at 100 megahertz. So the reference clock input here for this PLL, if we want to hook it up directly to the system clock, has to be 100 megahertz. I'm telling you this because when I was playing with this yesterday, I made the mistake of thinking that the system clock was running at 50 megahertz. So I put the reference input to this PLL at 50 megahertz and asked for 100 megahertz output, and I got a 200 megahertz clock. And I couldn't figure out why. And then I looked more closely at this system clock here and realized that actually this is running at 100 megahertz. Just be slightly careful of that. We hook up our reset lines as usual to the ARM and the system resets. And then we just, this is going to be our output clock. This will be basically what we replace clock 50 with. We can export that into our Verilog. And then there's an optional second conduit called locked, which is, you can turn off if you want. I don't end up using this in this example, but it is, I believe, just telling you whether or not the PLL is in a locked state. Maybe useful to you, maybe not. I haven't found that to be a useful piece of feedback for me, but you might. But in any case, we add this to the bus, save it, and then generate the HDL as usual. And when we do so, I'll look back at the computer system.v file. And just like when we exported PIO ports as conduits into the Verilog, we'll see a new signal appear within that computer system.v file that we can tie to our own Verilog in the computer system module instantiation at the bottom of our top level module file and clock off of that. And we'll get a faster clock as a consequence. So once this generates, I'll show you that.
Hunter, can you quickly explain why it's called a phase lock loop? I've never really had experience with it, so just wondering why they called that.
Bruce, do you want to answer that?
So a phase lock loop is an analog control system that's designed to keep the phases of two signals constant with respect to each other. And the way it works, I mean, this is a little harder to do with just waving hands in the air, but the input frequency is multiplied by the output frequency to make a difference frequency. That is then integrated and used to control a voltage controlled oscillator, which produces the output. And as a result, you're getting an output signal which is not only frequency locked, but phase locked to the input. That's why it's called phase lock loop. The tricky thing here is, what happens if you put a divide by 10, say, in the feedback from the output to the phase comparator? Now the output has to clock 10 times faster so that the feedback loop keeps the fedback divide by 10 signal in phase with the input. So if you divide the output by, if you feed back 1/10 of the frequency as the output frequency, then the overall phase lock loop multiplies the input frequency by 10. So it is a frequency multiplier. There's no other way to do it that I know of. The interesting thing about these phase lock loops is they will do fractional frequency multiply. Any rational fraction with no more than 6-bit accuracy in the numerator and denominator can be synthesized. If you want more information than that, we'll have to draw it. It's a control loop.
Are there any constraints in how much you can multiply your input?
Well, that is easy to look up in the PLL manual, of course. And it will, if you do something that's not allowed, it won't allow you to build it.
Thank you.
But there is on the page, on the course page, which is IP module index, there is a section on phase lock loops.
Any other questions? Okay, then I can continue going through sort of the mechanics of how you add this. If we open up the computer system.v file, we will see, as expected, a new signal has appeared here, which, well, two new signals have appeared. One which is PLL0 locked export, and the other which is the out clock, which will actually hook up to our Verilog. So I will, just like we do for the PIO ports, I'll copy these, add them to our module. Like so. And then again, as before, we'll tie this to our own wires that we'll declare in the Verilog above. So I'll call this one locked, and I'll define it in a moment. And I'll call this one my clock. And then up here, if I declare those two wires, wire locked and wire my clock. I can then, if I would like, change this Verilog so that instead of clocking off of clock 50, I can instead clock off of my clock. And now instead of running at 50 megahertz, this will run at the frequency that we specified in QSYS, which will be 200 megahertz. And I have a compiled version of this project that I'll load on the FPGA and show you that it does indeed blink faster. Precisely as much faster as you would expect. So pretty simple, and an easy way to get yourself extra cycles between audio samples. It will break at some point, which is to say it will, there will be some upper limit to the speed with which you can run your state machine. And you can incrementally work your way up to whatever that limiting speed is. But you should work your way up directly to that limit to build the biggest drum that you can.
Is there any benefit to doing this on the 50 megahertz clock as opposed to the 25 megahertz clock to get more granularity?
Not sure I understand the question.
Is there a 25? I didn't think there was a 25 megahertz clock input to this into the FPGA. I thought.
Oh, that's okay. That might just be the thing we use in Model Sim.
Yeah.
Yeah, I
Okay,
believe that all the clocks here are I think there's 450 inputs.
Oh, okay. Never mind.
Granularity is pretty good. If you try and set up 25.1 what is it 165 for 25.175 for a true VGA clock, you will get it. Because again, it'll do any rational fraction of two 6-bit integers.
We're going to do that either next lecture or the one after that, when I go over a module that directly drives the VGA screen without communicating through the Avalon bus. You need to create a 25 point something megahertz clock to do that, and you do that with one of these PLLs. Okay. So that is how you set one of these up on the bus. I want to show you one other option for doing this, which is if not useful, even if you don't use this method to actually set up one of these clocks, I think it's instructive to see that you can do this sort of thing with QSYS. So let's now suppose that we're going to set our reference. I want my reference clock here to be clock 50. I want to clock this off of clock 50. So I want my reference clock to be 50 megahertz. And I want to produce a 100 megahertz output from this PLL. So that's what I'm going to add to this bus. In order to do that, I want to hook up my reference clock to clock 50. I can export all of these to Verilog. And then I can make all of these connections within Verilog as opposed to here in QSYS. So if I generate this, and I'll just jump over to the completed file to show you this, but if I were to generate HDL for this QSYS arrangement now, within the computer system, oops, that's the wrong one. Within the computer system.v file here, we would see signals for each of those lines that we just exported, which would no longer just include the lock output and the clock output, but also reset and reference clock. So that then in our own module here, we could tie down in the computer system module instantiation, we can tie the reference clock directly to clock 50. Show you that in a moment. So this is just to make the point that you can make those reference clock connections in QSYS if you would like, if you hook it up to a clock that is visible on the QSYS bus, or you can export all of those signals into Verilog and make those connections in Verilog if you would like. We did something similar when we were controlling Avalon bus masters from the HPS. We would export signals into Verilog and make connections in Verilog as opposed to in QSYS. And I'm just making the point that you can do that with these PLLs also if you would like to.
So the system PLL here is the reference clock is connected in the Verilog, not the QSys, right?
Yeah, so let me show you in the, so in this particular file, this is the fully built version of the project that I'm incrementally building up. But down here in the computer system, these are the signals that got exported for the PLL for which we exported all of the signals into Verilog. So when we hooked up the first PLL in QSys, we only exported the lock signal and the output clock. And then we hooked those up to our own Verilog. In the case that we export every signal, we get the lock and the clock output, but we also get these signals, which in the previous example, we hooked up in QSys. We get the reference clock and we get the reset line. And I'm making the point that we can now hook up this reference clock directly to clock 50, and we can hold this reset line low, which is just to say it's not in a reset state, the clock is running. But this way we can clock our reference input to this PLL can be a 50 megahertz line as opposed to a 100 megahertz line. Okay. And then the final method that I want to show you is, there's no way that you would use this method just to set up a PLL. That would be kind of silly, but for your final projects, it may be the case that you want to build your own system that you can put onto the QSys bus. You may want to build your own custom system in the way that the audio system is a system that you can put on the QSys bus. And I want to show you how to do that. And the system that I'll build will be a very simple one where the only thing that it does is generate a PLL, but you could add more complexity to that system if you wanted to. So within the computer system, or with Open the Computer System QSys module, I can go to File, New System. Yeah, I'll save it. Okay. And the only thing that's in this system is a clock source. And then as before, I can add a PLL to this system. I'll say that the reference clock frequency is 100 megahertz. And I'll say that I want my desired frequency to be something different, 300 megahertz. Finish. And then I can hook this up within this subsystem. So I'm going to hook my reference clock up to the clock output of this clock source module here. I'll hook up reset to the clock reset, and I will export these two as conduits. You can take a look at this clock module here. The clock frequency that this is going to output is 50 megahertz. And I am going to if we look at the details here, that clock frequency is saying, clock frequency is known, says if set, the frequency is known. If not set, the frequency will be set from outside the system. So this is to say that I'll hook up some external clock to this, and I'll tell the system what its clock rate is going to be, as opposed to telling it that I know what its clock rate is going to be. I can save this. I'll call this something like my PLL. And when we save it, it generates within the Verilog folder for our project. It will generate a new folder here called my PLL, which has a whole bunch of Verilog in it. But what's interesting about this is if we open back up our computer system, we can now, if we would like, under the system here, we can add this system that we just created to the computer system module. And hook this up. So again, this is and export these. This is, you would not do this to create a PLL, right? If you wanted to just create a PLL, you'd probably use the first method for doing so is the easiest, which is just to add one of these things to the QSys layout, hook it up to the system clock, set your reference clock input to 100 megahertz and set your output to whatever you would like for it to be. This second option was just demonstrating that you could make those connections in Verilog if you wanted to. And this third option is demonstrating that you can build your own system, sort of you can build a QSys module that is one level of abstraction lower and then add that custom system to the QSys bus if you want to. So I could generate the HDL here and then recompile the project. I've done that in advance. So I'm going to close this. And open up this other project, which if we take a look at the QSys here. The Verilog here is quite simple. All that I've done is we have the Verilog that we started with, which was just flashing an LED at approximately 1 hertz using clock 50. And then I used almost exactly the same Verilog to flash the LED next to that LED off of a 200 megahertz PLL. The LED next to that, I am clocking off of a third PLL, another one that's at 100 megahertz, but that was generated using a different method. So to demonstrate that we can get the same PLL using either of these 3 methods. And then a final one here that is built using the custom subsystem that also generates a PLL. And this one will flash at I think I set it to 300 megahertz. In any case, the QSys layout is exactly that which we've just built. So I'm going to load this. And you can see we started with approximately 1 hertz flash of the bottom LED, LED 0. The LED next to it is flashing at 200 hertz. The LED next to that one is flashing at 100 hertz. The final LED is flashing at, I believe, 300 hertz. In any case, it's demonstrating that we are getting the appropriate flash rate in accordance with the frequency of the PLL that we've set in QSys or in Verilog. Any questions here? So what you should take away from this is when you're building your drum, you're probably going to want to clock your state machine not off of clock 50, but off of some faster clock. And in order to generate that faster clock, you make a phase-locked loop. To add a phase-locked loop to your design, you can do that in QSys. And I would recommend doing so with the first method that I showed you just because it's easiest. But I wanted to show you that there are a few methods that you could do this. And if down the road for your final projects, you wanted to make your own system within QSys, I also wanted to show you how you could go about doing that sort of thing. Okay.
At the risk of being confusing, you can also build a phase lock loop without using QSys at all. But then you have to look at the Altera IP library, which you can get to from Quartus directly. I'd use the QSys IP myself. I brought up
Okay.
I have a, if I can share a screen for a minute, I have a block diagram of phase lock loop.
Yeah, I'll stop sharing so that you can.
Right now. Now I can. So the basic phase lock loop is an input frequency, an input divider, divide by n, that's just a bunch of flip-flops, a phase detector, a voltage controlled oscillator, a divide by m counter in the feedback loop, and a divide by k and a divide by v counter in two of the outputs, so that you can set the output frequency is given by, does it say here? It's F out is equal to F in times M divided by N times K. You can go crazy kind of trying to figure out what's possible and what's not. It is a feedback control loop. You can cause it to fail. And one thing, the lock output tells you when this phase detector is stabilized.
Okay. The next thing that I'm going to talk about that I'll save for next time is going to be shared on-chip SRAM between the FPGA and the ARM. I will save that, like I said, for next time to talk about, but in the time that does remain, I will point out a few things within QSys that might be of interest to you. In particular, for Lab 2, you can expect, once you build a drum that's pretty big, you can expect very long compile times. You might be compiling for up to an hour in some cases. You can reduce that a little bit if within tools here, there is a drop-down menu for advisors. And if you take a look at the compilation time advisor, this will give you a bunch of suggestions for how you might be able to reduce your compilation time. Now, the fraction by which you'll actually be able to reduce it, I'm not sure. I don't know if you get a 10% faster compilation time or exactly how much faster it is. It'll be a little faster at the cost of, I believe, timing. Doesn't come for free, right? But this is a method by which you can ease your suffering a little bit.
What do you mean by at the cost of timing?
What that means is that the F max, the maximum frequency at which you can run the system, goes down. Because the compiler doesn't try as hard to squish everything together on the FPGA.
I was just speaking for like intermediate things as opposed to our final like max nodes step.
Yeah, right. And yeah, I for testing, for testing small systems, for 10 by 10s or 20 by 20s, definitely you want to speed up compile.
Any other questions? Okay. It's just to sort of get you to start thinking a little bit. I'll point out that we're maybe 3-ish weeks away from final project proposals. So still some time, but if you want to just start mulling things over and kicking around some ideas, on your own or with us, it might be about the time to start doing that. Particularly now as we've sort of gotten a sense of what we can do with the FPGAs and a sense of what some cool projects might be. Just start mulling it over. Okay. If any other questions pop up, just post them on Piazza, and I'll see most of you on Friday.